Hello students, in this video I am going to explain the magnetic effect of electric current. Okay, let's start children. Magnet, what is magnet? It is an object that attracts the objects made up of iron, cobalt and nickel. Okay, so it has some properties like it comes to rest in north-south direction children when suspended freely. If you take a magnet and suspend it freely, it always rests in north-south direction. Okay, and it has two poles children, north pole and south pole. We have learned in the lower standard that like poles repel each other and like poles attract each other. Okay, where we are using magnets children, let's see. Magnets are used in radio and stereo speakers, in refrigerator doors, on audio and video cassette players, on hard disks and floppies of computers, and in children toys. So these are the main applications of magnets. Now, magnetic field. What is magnetic field? Sometimes they will ask you define magnetic field of a magnet. So the area around a magnet where magnetic force is experienced is called a magnetic field. It is a quantity that has both direction and magnitude. Okay. So magnetic field is the region around a magnet where its influence can be exerted, children. Okay. So that we can say. So next, to represent the magnetic field, okay, we are representing with the help of magnetic field lines actually. Okay. Let's see what is magnetic field lines. Here, now the diagram is there. Okay, magnetic field lines. The magnetic field is represented by field lines. They are lines drawn in magnetic field along which a north magnetic pole moves. Okay, and magnetic field lines are called as magnetic lines of force also. See what happens. Let's take this is a magnet, north pole and south pole. So what is magnetic field lines? If you keep a magnet, okay, uh, what will happen if it move in a particular direction? So that will show the direction of magnetic field line. Okay, so generally the direction of magnetic field lines start from north pole and to the south pole. You can see from here in this diagram. Okay, field lines around a bar magnet. This diagram. Okay, it starts from north pole to south pole. Okay, north pole to south pole, and within the magnet it is south to north, children. Within the magnet it is south to north. Okay, you can see north to south, north to south. Outside the magnet, north to south. Okay, sometimes they will ask you what is magnetic field lines. State its properties. Okay, so what are the properties? Let's talk about the properties, children. Properties of magnetic field lines. They do not intersect each other. First of all, they never intersect each other. Okay, it is taken by convention that magnetic field lines emerge from north pole and merge at the south pole. Inside the magnet, the direction is from south pole to north pole. Therefore, magnetic field lines are closed curves. Okay, try to understand, children. Okay, it is a closed curve. It is a closed curve. It means if it starts from, okay, if it starts from north pole, if it starts from north pole into the south pole, again south to north, it will form a curve. It will form a closed curve actually. And one more thing is there, if you draw a tangent at any particular point, that will give you the direction of magnetic field. So to know that, if you draw a tangent at any particular point, so that will give you the direction of magnetic field. That is also important. Okay, is it clear? Next, magnetic field lines due to a current through a straight conductor. So I'm going to show you how it is. Okay, what I was telling that magnetic. Let's take a magnet is there, north pole and south pole. The direction of magnetic field starts from north pole into the south pole. Yes or no? Like this you see. Okay, it is outside the magnet, and within the magnet, how it is? Okay, within the magnet, it is south to north. So it start from north pole into the south pole, and it is within the magnet, it is south to north. Similarly, from here, start from north pole into the south pole, and it is complete this loop. It is south to north. Is it clear? So what I was telling, if you let's take this point A is there. You want to know the direction of magnetic field. So draw the tangent at this point. Okay. Draw the tangent at this point. So that will give you the direction of magnetic field line. It will give you the direction of magnetic field. Suppose at this point I want the direction. What is the direction of magnetic field at this point Q? Let's say this Q is there. So you have to draw the tangent. So tangent at this point will give you the direction of magnetic field. One question they are asking, why magnetic field lines never intersect each other? Assume that let's take a okay, they are intersecting at point suppose P. Okay, so this is the magnetic field lines and this is another magnetic field lines. So if they are intersecting at point P, so for this curve children, let's say this curve is XY. For the curve XY, the tangent will be along this direction, yes or no? Correct or not? The tangent will be along this direction. And for this curve, let's say this is CD curve. For this curve, where is the tangent? In this direction. So there will be two direction, okay, of magnetic field lines. So which is not possible. Okay, so that's why magnetic field lines never intersect each other. They cannot intersect each other. Okay. So this is the question they're asking in 2 marks. Okay. Let's talk about magnetic field due to a current carrying wire. Magnetic field due to a current carrying wire. Let's talk about magnetic field due to a current carrying wire. Okay. So let's take a wire is there which is carrying current. What is there? Magnetic field is generally represented as B children. Okay. So at a point, let's take D from the wire, magnetic field is produced. Okay. So magnetic field produced is directly proportional to the current. It means if current is more, magnetic field is also more. First concepts. Second concept is what? It is inversely proportional to the distance. D is the distance from the wire. Okay. It means if the distance from the wire is more, magnetic field is less. If distance from the wire is less, okay, magnetic field is more. Actually, there is an expression, children, that you can remember. B is equal to mu naught by 4 pi twice of I by D. Okay, that you learn in higher standard. So for your standard, you can just remember magnetic field depend upon two factor. One is the current, other is what a distance from the wire. Okay. Next concepts of magnetic field due to. Okay, now we will learn the direction of magnetic field lines. Direction of magnetic field lines by right hand thumb rule. Direction of magnetic field lines. Field lines. Okay, so I'll show you the statements written. Wait 1 second. Here you can see here magnetic field lines due to a current through a straight conductor wire. Okay, consist of series of concentric lines. Okay, concentric lines whose direction is given by the right hand thumb rule. So right hand thumb rule, you see right hand thumb rule. Okay, right hand thumb rule states that if a current carrying straight conductor is held in your right hand such that the thumb point towards the direction of current, then the wrapped finger shows the direction of magnetic field lines. Okay, let's check. This is the conductor, children, and current is going from top to bottom. So you hold the current carrying wire in such a way that the thumb points the direction of current, then curling finger point the direction of magnetic field lines. So here you can see this curling finger is what clockwise. Okay, it is what clockwise. So yes, this is according to the right hand thumb rule. It's going to show you here also. You can see. So you can see here also. Okay. Suppose this is the wire and current is going from bottom to top. Let's say A and B. Current is going from bottom to top. So you have to place your thumb, okay, in this direction. So, and if you draw the curve lines actually. Okay, it is concentric circle actually. Okay, so it will be the if you place the thumb here and that AB point the direction of water current, okay, the thumb, then the curling finger, it will be anti-clockwise, children. It will be anti-clockwise. Okay, it is anti-clockwise. Can draw like this. Okay, anti-clockwise. Okay, like this. So this is the direction of magnetic field lines using the right hand thumb rule. If the wire is like this is what a right hand thumb rule. Right and thumb rule. Okay, if the direction of the current is down, so it will be clockwise. It will be clockwise. One more rule is there, children, clock face rule. That also very, very important. Clock face rule. Okay, this rule states that, okay, if in the circular loop, the direction of current is clockwise. Okay, if it is clockwise, it behave as what a south pole. Okay, and if the current is flowing anti-clockwise, it behave as what a north pole. That clock face rule is also very, very important. Clock face rule. This is called as clock face rule. CLOCK, clock face rule. Okay, it means if in a closed loop, okay, in a circular loop, if the direction of current is clockwise, it behaves as south pole of a magnet, and if it is flowing anti-clockwise, it behaves as a north pole of a magnet. Now let's talk about the magnetic field due to a circular wire carrying current. Okay. Magnetic field due to a circular wire carrying current. Okay. Carrying current. Let's take, children, a circular wire is there in which current is passing. Okay, so it also produces magnetic field. It also produces magnetic field. Okay, current is flowing through this wire. So here magnetic field is also directly proportional to the current, and it is inversely proportional to the radius. Okay, so that is that the two things. And to know the direction of magnetic field, you have to use the right hand thumb rule. At this point, you can see current is going upward, so it will be anti-clockwise. Anti-clockwise. Now from this one is going downward, so it will be what clockwise, like this you can see. Okay, so use the right hand thumb rule to know the direction of magnetic field lines. Okay, similarly we talk about solenoid. What is solenoid? Okay, and how is the magnetic field due to a solenoid? So solenoid is a circular loop having n number of turns. You can see like this. Solenoid is there. Okay, let's take we connect to a shell. Okay. Now, what are the magnetic? Whenever current passes through this, it also produces magnetic field. Here, magnetic field is directly proportional to the number of turns. Okay, N is the number of turns in the solenoid, and also directly proportional to the current, children. It means if the number of turns is more, magnetic field is more. First condition, and second condition is what? If the current is more, magnetic field is also more. Okay, so they will ask you draw the pattern of magnetic field lines due to a solenoid. So let's talk about this. So if you take this as positive, children, this is negative. Okay, so current will be entering what clockwise here. Okay, yes or no? So if you see here like this, and what I have shown here, this current is entering like this. Okay, now so if you observe from, if any observer is here, so you will find that that current is entering like this. Yes or no? Clockwise from here. So it we have as what a south pole. Yes or no? And this side is what obviously north pole. Okay, so you can take this is south pole, this is north pole. Now this behaves as what bar magnet. So the direction will be what from north pole to south pole, north pole to south pole. Outside the magnet and within the magnet is south to north. So they may ask you to draw the pattern of magnetic field lines due to a solenoid. Okay, so I'm just going to show you this notes. Okay, this is the direction of magnetic field due to a circular loop. You can see this is a diagram which they have drawn in the NCERT. Okay, so you can see current is entering. Okay, and this is positive, means current is entering from this direction. You can see here. Okay, so here it is going like this, and I apply the right hand thumb rule to know the direction of magnetic field lines. Here also apply the right hand thumb rule. It is in this direction, correct or not? It is leaving from this point Y. This is X point. It is entering. So you have to use the right hand thumb rule to draw the pattern. Okay, and here you can see here strength of magnetic field lines. Okay, at the center of loop depend upon the radius of the coil. As I told you, the strength of magnetic field is inversely proportional to the radius of the coil. If the radius increases, the magnetic strength at the center decreases. Next, the number of turns in the coil. As the number of turns in the coil increases, the magnetic strength at the center increases because the current in each circular loop is having the same direction. Thus, the magnetic field due to each turn adds up. And the strength of current flowing in the coil also it depends. Okay, as the strength of current increases, the strength of magnetic field also increases, which I discussed to you before only. Okay, next we talk about solenoid, children. Here you see what is the solenoid. I told you a coil of many turns of insulated copper wire wrapped in the shape of cylinder is called as solenoid. The magnetic field produced by a solenoid is similar to the bar magnet that I have shown you also, children. The strength of magnetic field is proportional to the number of turns and magnitude of current. Okay, what happens, children, if you put a soft iron core, so it behaves as an electromagnet also. What is electromagnet? Electromagnet consists of a long coil of insulated copper wire wrapped on a soft iron core. Okay, so this is a diagram of electromagnet. You can see, children. Okay, to know the direction of force, we are using Fleming left hand rule. Try to understand this rule. Very, very important. Sometimes they will ask for 2 marks. So stretch the left hand. You can see this is the left hand. Stretch the left hand thumb, forefinger and central finger in such a way that they are mutually perpendicular, okay, to each other. So forefinger points in the direction of magnetic field and the central finger in the direction of current. Then the thumb gives the direction of force acting on the conductor. So this is the field, children. The field is upward. This is towards the right side. Okay, current, and then the thumb points the direction of motion. So this also question they ask for 3 marks. Can show like this also. Field, force and current. So they must be mutually perpendicular to each other. Okay. It is used to generally find the direction of motion of the conductor. I hope you understood this concept, children. Please share with your friends and subscribe the channel. Thank you.